Hi, I'm going to be talking about term symbols for electronic transitions. So I'm not having you do any of the homework assignments over term symbols. You can use them in some of your interpretations, but I wanted to make sure that you were familiar with them. I know several of you are going on into graduate school, specifically in synthesis, as well as spectroscopy, and so it would just be really good for you to have term symbols. Cool, and I think it's a great way of thinking about angular momentum. So think of the molecule. And so that I've got a diatomic here. So think about everything we know about that diatomic. Orbital, or actually, I'll start with this. H psi equals E psi. We have a wave function representing the molecular orbital, which is a linear combination of atomic orbitals from the orbital approximation of hydrogenic atoms. Combine those together in a linear combination, you get a wave function, and that's going to yield rotational, vibrational, electronic, nuclear energies. Based on the Born-Oppenheimer approximation, you can separate those out. So a lot going on here. But one of the things that I want to talk about is specifically the angular momentum associated with this molecule. Now, if a photon comes in, the only way that a photon is going to interact with this molecule is if it transfers its angular momentum. And so you've got spin equal to 1 for a photon, spin 1/2 for electrons. So if you're going to have an electronic transition of this system, you need to have spin 1 convert or somehow transfer to spin 1/2. And that's where electronic transitions are a little strange. So I want you to think about the total angular momentum. So the angular momentum specifically of this whole electronic system, which could have p orbitals. So the angular momentum projected onto the internuclear axis. Okay, we've spent some time talking about how we can have an orbit and there's going to be some sort of angular momentum L, and that's going to be projected onto the z-axis. Okay, so you're happy with this, hopefully. Well, now we're talking about projections of angular momentum of the electrons around. So say there's an angular momentum like this, there's going to be a projection onto, so if that's our angular momentum, there's going to be some projection down onto that internuclear axis. Sound good? Okay, that's what the term symbols are going to be representing. Because if you think about the electronic configurations that you've known for so long, 2, 2s2, those don't help us out when we're talking about the specific energies of the electrons in a molecular orbital. That's where you'd want 1 sigma 2, 2 sigma 2, 3 sigma 2, 4 sigma 2, 5 sigma 2, 1 pi 4, and so on, where those are your 1s, 2s, and 2p. Cool? Okay. So what term symbols are going to do is it going to specifically tell you which, once these are in these molecular orbitals, which electrons are the ones that are going to undergo the transition. Okay, I'm just going to jump to what they look like. So we have 2s plus 1 multiplicity, like we know before. The total angular momentum projected onto this z-axis, plus or minus, depending on the parity. If these lobes are plus and minus, which lobe is the electron located in? And then this represents the sum, the total angular momentum, and then we've also got Gerada or Ungerada to designate the symmetry. Whew, that's a lot. So let's break this down. Let's start with this one. So lambda is equal to that projection right here, that's lambda. Go team. So if lambda equals 0, we're going to call it a sigma orbital. If lambda is equal to 1, we're going to call it a pi orbital. If lambda is equal to 2, we're going to call it a delta orbital. So you may have seen something that looks like this, 3 sigma plus. That's a term symbol that we're going to be dealing with. Okay. But lambda also equals lambda 1 plus lambda 2 plus lambda number of electrons that you have. So for every electron you have in your system, it's going to represent, so if you have, so this could be plus or minus 1 if the electron is degenerate in a pi orbital, which means it could be, it's a plus 1 if it's the plus parity. It could be a minus 1 if it's minus parity. Cool. But if electron is in a sigma bond, there's actually no net angular momentum around the orbital, so there's no projection. So sigma bonds, angular momentum is 0. Sigma. Angular momentum is 1, pi. Angular momentum is 2, delta. Okay? Cool. And this is very, I just read Atkins and I wrote my notes. So if you watch this and then read Atkins, hopefully it'll make more sense. Okay, this S here. So when you have your electron, actually, let me do an example of oxygen real quick with the lambda. That way we'll have some context to what we're talking about. All right, so we're going to do O2. So the molecular electron configuration for oxygen is 1 sigma G2, 1 sigma U2, where this is the antibonding orbital, 2 sigma G, 2 of those, 1 pi 4 Ungerata, 1 pi Gerata 2. Awesome. So these and this are my antibonding orbitals, bonding, bonding, bonding. Cool. Okay. Crap, I need to get more. It's like 9 o'clock at night and the baby's asleep, so I'm enjoying a beer. Okay. I enjoyed a beer. It's now empty. Okay. So this, if we're going to have a photon interact with any of the electrons, most likely it's going to be the valence electrons. So we only care about that one. That's what these are going to represent. All right, so we are in a, so 1 pi 2 G. That says we have 2 electrons, which means in a pi orbital, which means lambda 1. So one of the angular momentums of one electron is equal to plus or minus 1. We don't know if it's in the plus or the minus lobe of a p orbital. And so then the other one, lambda 2, is in the plus or minus 1. Go team. Which means if big lambda is equal to little lambda 1 plus lambda 2, lambda can equal plus 1 plus plus 1, which equals 2. It can also equal minus 1 plus minus 1, which equals minus 2, if we have them both in the plus and the minus and the minus. Okay? If that's the case, then that means that my electrons are, so if that's the case, oh, I should also say this is the magnitude of big lambda. So we've got 2 and minus 2, which means that we're going to have a delta. Cool. So I'm going to write delta. All right, so I know it's that one. But the electrons are in a p orbital and unpaired. So this 2s plus 1 equals the multiplicity, just like we've learned before, but s, because the electrons in this case are unpaired, that means that so the multiplicity is the number of unpaired electrons plus 1, and there is only one unpaired electron, or sorry, the electrons, if they're in the, sorry, let me try this again. If they're in the same orbital, then you'd have, if they're in the same orbital, then that means that the S is going to be 0 because, whoops, electrons are paired. There we go. So that one would be both spin up, spin up, spin down, spin down. That makes more sense. So that means that they are paired. Okay, so if that's the case, then that means that in order for this S to be 0, so 2 times 0 plus 1 equals 1. Okay, so there's only one possible orientation of this angular momentum from the spin, which means that this number is going to be 1. 1 delta. Go team. So that's the term symbol if we have the electrons in the same p orbital. All right. If, however, they are in different p orbitals, I'm going to get rid of this. I'm going to get rid of this. Actually, I'm going to say lambda equals 0, 1, 2, sigma, pi, delta. So if lambda 1 equals plus 1 and lambda 2 equals minus 1, other things happen. So big lambda equals 0 if that's the case, because 1 minus, so plus 1 minus 1 equals 0. So and the electron spins can either be up, up, down, down, or up, down. So you have 3 options. In these two cases, S equals 0. But in this case, S equals 1. Go team. Therefore, you have, so because lambda equals 0, this means that the term symbol is going to be the sigma, and 2, 0 plus 1 equals 1, and 2 times 1 plus 1 equals 3. Therefore, we have a 1 sigma and a 3 sigma, to where both of these fall under the 1 sigma, because if you have spin up, so that would be that this one has a spin up and this one has a spin up, and it would be that this one has a spin up or spin down and spin down, and then this one is that they are both occupying spin up and spin down in the same orbital. Okay. And then you would add the spins, so it'd be a half plus a half gives you a whole half, or gives you half plus a half gives you a 1. Okay. So the term symbols for O2 are sigma 1, delta 1, or 3 sigma. So those are the 3 that you could get. And it turns out that that is the lowest energy. More experiments to follow. Okay, so that is the lambda portion. So now let's talk about, so we got that half. Now let's talk about this and that part. I'm going to pause and erase everything. Pause and erase. Okay, so now I'm going to talk about this lambda and the plus minus, and this has to deal with symmetry. Now we've skipped the chapters in Atkins that talk about molecular symmetry, i.e. group theory's application. Group theory really is a way to solve this. If there's overlap, bonding. If there's no overlap, no bonding. No bonding, bonding. So group theory is a way to identify the aspects of symmetry adapted linear combinations of linear combinations of atomic orbitals, and then you adapt them in terms of their symmetries, and you can solve these a lot of these by just recognizing that it's C2V symmetry or it's DH symmetry. And so group theory is one of the most powerful mathematical applications we have to chemistry. And it's quite remarkable how beautiful it matches. Group theory was developed completely independent of chemistry, and when people figured out that it could be applied to solving these quantum mechanical systems, oh my God. So much so that when you go to, sorry, not when, if you go to graduate school specifically in chemistry and you do organic synthesis with any sort of spectroscopy, or you're a physical chemist, group theory and symmetry is a required class. I mean, my class was quantum, stat mech, symmetry. 1 and 2 of each of those were my graduate student or my graduate classes. Anyway, so it's quite beautiful. That's where these are coming in. The symmetry arguments and then Gurada and Gurada are based on symmetry. So if you learn the term symbols, it will help you in understanding symmetry. This is one of the reasons that Graham and mine's class is so closely connected. All of my class can fit in the first week of Graham's. If you look closely and go back and reread your inorganic textbook, just reread I think it was like chapter 3. The first paragraph, that's this entire class. It's kind of cool. Okay, so although we obviously go deeper, but so for diatomics, I should also mention if it's not diatomics, it gets a little bit more complicated, but good approximations. Okay, so a diatomic is going to have a mirror plane. And if I have a sigma bond, so if the mirror plane would be, if this was me standing here, then me standing there would be this. Okay, a mirror plane. So there's a mirror image underneath. So if you flip it over, that's what you get. So if I have a sigma bond that has positive parity, if it has a reflection through that mirror plane. So sigma bonds are symmetric upon inversion. Which means that they get a plus. Yay, they get a plus. So lambda plus, so whatever lambda might be, sigma, pi, delta, they get a plus if it's a sigma. Woo, although sigma would most likely be that, because you aren't going to get a pi and a delta if it's a sigma bond. Okay, at least I'm not sure. If I'm wrong, let me know. Go team. If you have p orbitals, plus, plus, minus, minus, what happens when you do an inversion here? It flips. It becomes, this becomes positive, this becomes negative. So in that case, that's when you get a negative sign, if you don't maintain the parity upon inversion. Okay. The other thing that's cool is if you have a p orbital that is so if the p orbitals are into the plane, so the symmetry, so basically they're like this. So the plus and the minus and the plus and the minus, I can't do this. Okay, so there's my hand. So plus and minus, if they're this way and they're going this direction, so plus and minus and plus and minus, if these are into the plane, you're cutting them in half, so they're still symmetry. It's just like this one. Imagine there's a p orbital with a negative sign behind it. That's a positive. So you can have p orbitals that do have positive symmetry. Okay. Questions? Pause and email. I'm going to take a beer. This is a Keller beer, which is a young lager. Go team. Okay. Oh, this is really cool. Okay, this is my favorite part of term symbols. This guy right here. Let's go back over here. If you have, and this is just so wicked cool to think about it this way, these electrons are delocalized waves. There's waves everywhere, but all in one, essentially. So when you have a diatomic and you've got some angular momentum L, which is this lambda here. That's the angular momentum associated with the molecular orbital, okay? And there's going to be some projection onto the internuclear axis, and that's lambda, that projection right there. Okay, if, however, you have an additional spin, this is cool. So there's a spin contribution. Whoop. So there's a spin contribution from an electron somewhere. That means that you're going to get an extra sigma. Go with it. And these combined total angular momentum are going to give you the total angular momentum of your overall diatomic. Okay, so if there's basically spin orbit coupling occurring within the molecule, so there's an additional spin here, say there's a lone electron on one part of your molecule, then that additional spin is going to couple with this angular momentum, and then you're going to have an additional angular momentum that you can add together, and that's going to be your total angular momentum. That's wicked cool. Okay, on behalf of chemists, I am sorry. We have used sigma a little too much. We got excited. This sigma involves the spin contribution. Okay, so this is the spin quantum number. And that's why I've got little tails on it. That's different than this sigma. I'm sorry, term symbols are confusing, but with practice, they make perfect sense. Same thing, think about this. That makes sense now. It didn't when you first learned it years ago. Term symbols are the same way. Okay. So spin quantum number, sigma, you've got lambda there, and this represents, again, the projection of this angular momentum, and this is the angular momentum of the molecular orbitals, the spin contribution. You add them together, and you get this number, which goes here. Let me give you an example, which would be, do I have one? Yes, I do. NO, that's exciting. Sorry, not just like oxide, not no, I don't have an example. Okay, so let me do NO and then we'll stop because it's getting to be a long video. All right, I'm only caring for NO about the final valence electrons essentially. And so it has a bunch of molecular orbital configurations, 2 pi 1. Okay, that's the top one. All right, so there's one unpaired electron. So S equals 1/2. That's cool. Lambda equals, so there's just one electron. So this equals plus or minus 1 because we don't know. So lambda equals pi because lambda equals 1. So then we have omega equals lambda plus sigma. And since sigma, oh, I should add. Okay, so so there's our pi. Cool. So, and we've got, before I get to sigma, let's talk about S equals 1/2. So the number that goes here, this one, so 2 times 1/2 plus 1, that gives me 2 right there. So there's a multiplicity of 2, which tells me that there's 2 possible orientations, which is good because I have plus or minus 1 as my lambda. So there's my 2 possible orientations. So then now I'm going to find my omega, which is my angular momentum of my molecule with adding to my angular momentum of my additional spin projected onto the internuclear axis. And that gives me, so sigma can be found by the same as the Klebsch-Gordon calculation that we had for molecular orbitals. This equals s minus 1 all the way to minus s. And since s equals a half, we have 1/2 minus 1/2. Go team, because luckily 1/2 minus 1 is minus 1/2, and that gets me all the way to my minus s. So there's just 2, which I know there's 2 because I have a multiplicity of 2. Okay, so then I can say that omega equals +1 plus 1/2, which is 3/2, or it's equal to -1 plus 1/2, which is equal to -1/2, or I can say that it is equal to +1 minus 1/2, which is equal 1/2, or I can have one more combination. I can have, which one am I missing? -1 minus 1/2, which is equals -3/2. Everyone follow? Because for my lambda, I can have plus or minus 1. For my sigma, I have plus or minus 1/2, and so then I'm going to have 4 combinations, which means I take the absolute value of those, and I'm left with 2 pi 3/2, 2 pi 1/2, and each of those has 2 degenerate states. Hope y'all can read that. So 2 degenerate states. So there's a 2 3/2 and a, I'll make that bigger. So there's a 2 pi 3/2 and a 2 pi 1/2, with there being 2 of these and 2 of these. And it turns out that one's slightly lower in energy. Awesome. I have more notes and more examples. Oh, last but not least, why do we care? I should lead with that. So we care because of transition states, transitions, which give us selection rules. Okay, so for electronic transitions to occur, which is what I started to talk about, so the selection rules require that there's a change of the projection of the angular momentum, this, of 0 or plus or minus 1. There's a change in S, which is good. Actually, there's not a change in S. Delta S is 0. So we're maintaining the electron angular momentum. So there's no change in the electron's angular momentum. There is no change in the sum of the S's, which if this is true, this should be true. And then we've got that there's no change, or there's only a change of plus or minus 1 in the sum of the sigma, the S projection onto the angular momentum in the lambda, which if you think about it, if you're going to add these two together, you're going to get this rule. Go team. This is learned via application, but I want you to recognize the symbols, recognize that this is all about conservation of angular momentum of incident photon coming in. If you have unit photon or unit angular momentum spin quantum number of a photon coming in, it needs to transfer to its angular momentum to these electrons. And that only occurs under certain conditions of unit projection onto the internuclear axis. Go team. This is really cool stuff. Please use some of this when you're answering some of your homework problems, and email me if you have questions. Be well. Bye.